Thank you all for joining today for this webinar on model-based systems engineering, a beginner's guide. And although this is a beginner's guide, the goal is for new users as well as experienced users to walk away with some new information or a new perspective on model-based systems engineering. And with that, we'll jump right into the agenda. On the agenda today, we have the motivation for everyone being here. Why are we talking about model-based systems engineering? And after that, we'll be defining the term and moving into the pillars of MBSE, which are modeling language, tool, and methodology. After that, we'll be looking at the tool we support here at GoEngineer, which is Magic Cyber Systems Engineer, and how this can help you on adopting your model-based systems engineering methodology. After that, we'll talk about how this tool is really for implementation and not replacing any of your current methods. It's really for evolving your current digital thread. And finally, we'll close with a review and talk about the advantages of model-based systems engineering. So let's start off with the motivation for model-based systems engineering. And if you've heard anything about MBSE, you've heard the age-old cliche of complex problems, and that being the reason for adopting model-based systems engineering. But there are a host of reasons why you might implement a MBSE methodology on your projects, and we'll talk about some of those later. But of course, we have to talk about the world becoming more complex with your various stakeholders, firm deadlines, and of course, limited budget flexibility. There's also a need for future-proofing and integrating with other systems, as well as deriving those hidden requirements from these stakeholders that you'll have to derive through your system engineering process. And these complex problems lead to complex solutions, oftentimes multidisciplinary, multi-supplier, and multi-application. And so while on the outside the solution may look like a clean gear, we understand that once we dive into that, there are a lot of disciplines and a lot of stakeholders that go into creating this solution. And this is where model-based systems engineering really comes in. But maybe your system isn't this complex. Who is model-based system engineering really for? And what are some of the benefits? So if you're looking to do any impact analysis, simulated verification, or maybe even model reuse on some of your other projects, or model-based trade studies, model-based system engineering is definitely something that you should be looking into. And on the flip side, maybe you're having some verification gaps, late deliveries, or going over budget. Or maybe you have a lot of technical debt as you go throughout your systems engineering process. You might be over-designing or even have some gaps in your analysis. Model-based system engineering was developed to conquer all of these downfalls and really expand your capability as you go through your solution process. So now that we have a firm grasp on the motivation for adopting model-based systems engineering, we can move into defining that term, starting with model-based. And the easiest way to understand being model-based is to understand the traditional systems engineering method, which is being document-based. And we call it document-based. It's not pencil and paper, but it's really using software that is designed to create documents. In this example, we have our requirements held in an Excel table. And traditionally, you'll have your requirements with their text and some other columns representing other attributes that you want to tie along with those requirements. But this traceability can easily become corrupt or outdated. And so this is where model-based system engineering really comes into play. And so if we look at Magic Cyber Systems Engineer, we still have that traditional table format where you can import your requirements from JAMA, Doors, Excel, for example, or you can create the requirements directly in the software. And here we are looking at stakeholder needs. And from those stakeholder needs, we'll start to create these system requirements. This is a requirements diagram, which is another method for creating your requirements in the tool. And so once you have those created, we'll start to use some of the cross-cutting relationships to really understand the traceability throughout our requirement structure. Here we have our stakeholder needs across the top and our system requirements across the left. And we're creating that derived relationship to understand all of our traceability and understand that we have coverage for all of our stakeholder needs. There's also another view that you can use, which is the map view. This is an excellent view for doing impact analysis if there are any changes upstream or downstream through the system. And this is one of the great benefits of being model-based over a document-based system. But there are also benefits on the structure side. And so traditionally, you may have stakeholders or people on the team who can't really understand or visualize the system that's being built. And so you might go into a tool such as Visio or PowerPoint to build out that system structure, maybe starting with your system of interest, your subsystems, and then moving into your component level. But there are a few downfalls of this method. For one, there's not a common graphical language. You might use boxes here and somebody else might use circles or lines with arrows or lines without arrows. As well as once you create multiple documents to try to represent different tiers in your system, there is no traceability between that and there is no synchronization between that. So when there are changes in your system, you have to go through and really update every single document. And so this is where being model-based comes in on the structure side. And also there's no way to tie your requirements to your structure unless you use a tool like Magic Cyber Systems Engineer. And so if we look at this block definition diagram here, we can start to understand the system structure of our system of interest, which is the VCCS system. Anyone who understands SysML will be able to instantly come in and understand this language without needing any additional information. Additionally, there's the traceability on the structure side. And so if you want to understand how the cooling system and the CP system interact, we can dive into the internal block diagram of our system of interest to really understand the communication between the cooling and the CP system and any other subsystems in our system of interest. Another great benefit is the traceability from the structure side to the requirement side. And this is a major benefit if you house your requirements and your system structure in the same environment. And so finally, there's the synchronization throughout the entire model. If I wanted to update the name of the block that I have here in the center to include my serial number, anywhere that this block exists in the entire model will be updated to reflect that change. And so you'll never be out of date in understanding your system structure or your system requirements throughout the model. And those are the major benefits of being model-based over being document-based. You have the common graphical language, your model synchronization, as well as the collaboration between anybody working in the tool. You also have simulation, which we'll get into a little bit later, and the project reuse. And all of these benefits, of course, come with their complexities. There is the complexity of learning the graphical language. There are some great resources to do so. The tool learning curve, which implements the language. And of course, version control. You really need to have a system in place for your version and change control process before you start your model-based system engineering methodology. And with that, we can start to discuss systems engineering. And we can't talk about systems engineering without talking about NCOSE. NCOSE is the International Council on Systems Engineering, and they define it as a transdisciplinary and integrative approach to enable the successful realization, use, and retirement of engineered systems. So of course, the purpose of systems engineering is to engineer entire systems, facilitate conversation between disciplines, identify gaps, and of course do risk issue and opportunity management. Now, combining these two terms, NCOSE also defines model-based systems engineering. And they define it as the formalized application of modeling to support systems engineering. So the purpose of MBSE is to graphically engineer systems, integrate information from different disciplines using independent tools, identify gaps through graphical analysis and simulation, while still doing that risk issue and opportunity management just earlier in your systems engineering process. So model-based system engineering is designed to condense your risk phase to the system design phase of your systems engineering process. And this is done through tying all of your requirements and your system structure together and even doing some system verification through simulation before you even get to the detailed design process, product integration, or test phase. And so model-based system engineering allows you to save time and resources by dedicating more time to the system design process and condensing all the other phases of your system engineering process. And so now we can move into the pillars of model-based system engineering, which are modeling language, modeling tool, and modeling method. And we'll be starting with the systems modeling language. SysML is authored by the Object Management Group, or OMG, and they define SysML as a general purpose modeling language for modeling systems that is intended to facilitate a MBSE approach to engineer systems. So SysML is a graphical language and is composed of 9 diagrams. And this model wasn't built from scratch. It was built off of UML, or the Unified Modeling Language. This is the graphical language for software engineers. And so system engineers saw this and appreciated it and used some of the same diagrams, modified others, and created new diagrams for the specific purpose of doing model-based systems engineering. Of course, this comes with the great benefit of having a common graphical language, and that also offers its complexity of learning that language, which is a necessity for implementing model-based systems engineering. So the second pillar is the tool, and our tool of choice is Magic Cyber Systems Engineer. Is the tool of choice because one, of course, it is SysML compliant, and the digital thread readiness, which we'll dive into a little bit later. It has also become the industry standard, especially on the defense and aerospace side, and that is now transitioning to all industries that are implementing model-based system engineering using Magic Cyber Systems Engineer. Another great resource is the support. There is plenty of documentation on using the tool. The Magic Grid framework is actually a source of support as well for some simple tool navigation and procedures. And there is a great resource on documentation that DSO has on using the tool itself. And so this does lessen the tool learning curve by using these resources. And we'll kind of dive into how Magic Cyber Systems Engineer is language law compliant with SysML. And so if we look at this simple block definition diagram here, we have a couple of blocks, a couple of signals, and a couple of requirements. And as you can see, I'm trying to create a composition relationship starting from a requirement. And this is illegal according to language law. And Magic Cyber System Engineer will enforce that language law by not even allowing you to create that relationship. Now, if I come over to a block, it will allow me to create that relationship between any other legal elements in my system. The same for a derived relationship. It will not allow me to create a derived relationship between two illegal elements in my system. So I have to come over to another legal element and create that relationship in my system. And this is how Magic Cyber Systems Engineer enforces language law. And this is why we recommend Magic Cyber Systems Engineer for implementing your model-based system engineering methodology, which is actually the final pillar of MBSE. And the methodology that you choose to adopt might be the Magic Grid framework. And if you do, there are a couple of advantages to adopting this methodology. One, it is vanilla SysML compliant. That means that there is no need for additional plugins in order to use this methodology. It is also free to download on our website, and there is a sample model walkthrough that teaches you exactly how to use the methodology and use the framework that exists in this book of knowledge. There's also a completed version of that sample once you download the tool, and since there is a walkthrough, it teaches you some of that basic Magic Cyber Systems Engineer functionality, which will allow you to cut down on that second complexity of using the tool. And with all that being said, it is actually tool independent, as long as that tool does enforce the SysML language. So to conclude the pillar section, they are language, tool, and methodology. You need a common graphical language to build the models. You need the tool to enforce the language. And finally, you need a methodology that defines what diagrams should be created at each stage in your system engineering process. And so now that we have gone through the motivation, definition, and the pillars of MBSE, we can really dive into Magic Cyber Systems Engineer to see a lot of the capabilities that are offered whenever you download this tool for your model-based system engineering environment. Okay, here we are inside of Magic Cyber Systems Engineer 2024, and we are currently looking at the Magic Grid sample of the vehicle climate control system. As you can see here on the diagram pane, we have a graphical representation of the Magic Grid framework. Now, there are a lot more diagrams that exist within this model, but we'll be focusing on the ones here in order to get a better understanding of the Magic Grid framework, as well as look at some of the capabilities inside of Magic Cyber Systems Engineer. Okay, so as you can see, we have the domains on the left and the pillars across the top. Those include the requirements pillar, which will house the requirements diagrams, the structure pillar, which will house the internal block diagrams, block definition diagrams, as well as the package diagrams, the behavior pillar, which will house the use case diagrams, activity diagrams, state machine diagrams, and sequence diagrams, and finally the parameters pillar, which will house the parametric diagrams. On the left, there are the domains. Those include the problem domain, solution domain, and implementation domain. The problem domain is broken into the black box and white box domain. If you are not familiar with black box, this is treating the internal structure and behavior of the system as a non-factor. And so we'll be diving into the requirements pillar to start off in the black box domain. Again, you can import these or you can create them directly in the software. And now that we have those captured, we'll be moving over to the structure pillar where we'll be talking about the system context. The system context represents the environment that our system will be operating in. For this example, we'll be looking at the vehicle in use system context. And we'll be using an IVD to represent the internal structure of our vehicle in use system context. Here we have our system of interest interfacing with the temperature sensor, vehicle occupant, and cabin. And so now that we have the system context defined, we'll go back to our stakeholder needs to identify all our use cases that reside in that system context. As of right now, we've identified the provide comfortable temperature. That is what our system of interest needs to do in this system context. And we'll refine that with an activity diagram that shows all the functionality of our system of interest. And we'll need to refine these as we go through the methodology. As you'll see, moving forward, we'll be focusing on this reach desired temperature, and this rate details that there are more diagrams that lie within this action. And so now that we have those three pillars done, we'll move into our final pillar in the problem domain, being measures of effectiveness. Our measures of effectiveness were determined based on the stakeholder needs to be sound level, total mass, and total energy consumption. We'll use these to do trade studies and truly understand if our system of interest is meeting the stakeholder needs as they've been defined. And that concludes the black box domain. Now we'll move over to the white box domain. We'll be looking at the conceptual subsystems, functional analysis, and MOEs for the subsystems. First, we'll dive into an IBD as we are now concerned with the internal structure of our system of interest. As you can see, we have some part properties here that represent our subsystems, as well as the interaction between those subsystems and the exterior boundary of our system of interest. After that, we'll dive into our behavior. We can come through our use case diagram here and go through an activity diagram to find a final activity diagram of the reach desired temperature. Here we have all of our subsystems defined and the functionality that they should be completing as we go through our solution phase. And finally, we can move our MOEs down to our subsystem level. We have an MOEs holder, and we'll just use a generalization relationship to move those values down to all of our subsystems. And with that, we have concluded the problem domain. We have identified the stakeholder needs, captured the system context as well as the use cases in those contexts, and identified the measures of effectiveness which we'll use to do our trade studies and understand if our solution is meeting those stakeholder needs. We've also identified the conceptual subsystems, the functional analysis of the subsystems, and moved those MOEs down to all of our subsystems. Now we'll be moving to the solution domain. In the solution domain, we'll be identifying the system requirements based on the stakeholder needs, our system structure in more detail, system behavior, as well as the system parameters. So let's start with our system requirements. Here again, we have a requirements diagram where we have captured all of these system requirements. And since these were derived from our stakeholder needs, we'll use a matrix to make sure that we have that traceability down from our stakeholder needs to our system requirements. Again, we can also represent that in a map format to allow us to do any impact analysis for changes upstream or downstream. And moving on from the system requirements, we now have the system structure. For this level, we'll be identifying the logical architecture of our system of interest. Here we've used a block definition diagram to capture all of our subsystems, interfaces, and exchange items that are necessary to satisfy our requirements. Now moving forward to our system behavior. Usually at the logical architecture level, you do not identify the system behavior, but we can go ahead and jump into the subsystem behavior, which will make up our system behavior. Here we have some state machines identifying all the states of our CP system, as well as our cooling system to identify what functionality is available in those states. And finally, at this level, we have our system parameters. Our parameters have been moved down to our subsystem levels to do some calculation and understand if we are meeting those requirements. We can actually jump into a simulation at this point to have our software automatically verify whether we are meeting the requirements of our system. So, through the use of Magic Model Analyst, we have the ability to simulate this parametric diagram. And through the simulation, we can input values based on proposed solutions in our solution domain to understand if they are viable to meet our stakeholder needs or our system requirements. And if they're not, we have the ability to go in and find other solutions that do meet our stakeholder needs and system requirements. Now, at this point, you can move down to the subsystem or component levels to complete the solution domain, depending on the unique circumstances of your project. Now, the Magic Grid framework concludes with the implementation domain, which only covers the requirements pillar. This is because the later stages of the design process are better captured in tools such as SOLIDWORKS. But for the requirements, you can capture those here in a requirements diagram or a table. And once you do that and form the traceability throughout the system, you have completed the Magic Grid framework. Now, this concludes our demonstration of Magic Cyber Systems Engineer. Again, the Magic Grid Book of Knowledge is available for download on our website, and it will walk you through this tutorial to build out your system and compare it to the completed tutorial once you download the software. Now, there are a couple of options for expanding Magic Cyber Systems Engineer, one of them being the Magic Collaboration Studio. This acts as a repository for all your models on your servers, allowing simultaneous access from modelers and non-modelers alike. Now, another option is the Magic Model Analyst. This is the simulation plugin that allows you to perform gap analysis, as well as do some early simulation validation for your system. Now, model-based systems engineering is not about replacement, it's really about implementation. And this is where Magic Cyber Systems Engineer really shines. So your digital thread is what links and or integrates data generated from within or across disciplines using independent software tools. And Magic Cyber Systems Engineer has a host of integrations that are already existing to interface with your current tools. This is just a short list, and there's a full list that's available on their documentation page. You can just look up anything that you're looking to interface with. And to wrap it all up, model-based systems engineering will expand your system design process, allowing you to assume all your risks early on in the project when it's a lot cheaper to do so, while simultaneously contracting your detailed design, product integration, and testing phases, saving you a lot of time and resources over the life cycle of your project.